All right, like I was saying at the last lesson, let's get mathy. So, what we're going to do now is we are going to start doing calculations around solubility. So, this lesson is all about the solubility product. So, the first thing we're going to learn about is the solubility product constant. So, remember, we had the equilibrium constant, and now we have the solubility product constant. So equilibrium constant is KEQ, solubility product constant is KSP. So KSP is your solubility product constant. It is the equilibrium constant for an ionic substance dissolving in water. So it actually is the equilibrium constant, but we give it a more specific name because it's the equilibrium constant for this dissolving in water. Now, this only works for slightly soluble ionic compounds because they exist in an equilibrium between undissolved solids and dissolved ions. So we wouldn't want to do something that's completely soluble because it would be all ions and no solid, right? Or we wouldn't want to do this for something that doesn't even form any ions in solution or a negligible amount of ions in solution because, again, then it would be all solid. So we're going to be doing these things for things that have low solubility. All right, so because there's an equilibrium that exists between undissolved solids and dissolved ions, we can write an equilibrium expression called the solubility product expression. How do we do that? Well, when you're writing KSP, the first thing you'll start with is the dissociation equation. So this is calcium carbonate forming calcium and carbonate ions. And the KSP would be equal to the concentration of the products over the concentration of the reactants. So we've got calcium times carbonate, but you'll notice I didn't put it over the reactants. Why? Because my reactant is a solid, and solids are not included in KSP expressions, only aqueous. Why? Because the concentration of the solid cannot be changed, right? So this is the same rules that we learned in Unit 2, but just applied in Unit 3. So I want you to write the equilibrium equation and corresponding solubility product expression for magnesium hydroxide. So the first thing we would do is we would write the equilibrium expression or equation for magnesium hydroxide. So magnesium hydroxide would break up into magnesium ions and hydroxide ions, and you'd have 2 hydroxide. So the KEQ would equal the products, what was I going to say there? The product of the products? That felt really weird. Anyway, it's products of our reactants, but we're not going to include the reactant. So it's going to be the concentration of magnesium times the concentration of hydroxide, and don't forget whatever the coefficient on your ion is becomes your exponent in your KEQ. Oh, I wrote KEQ. That was habit. The KSP. I mean, are they the same? Are they different? Doesn't really matter. But let's make sure that we're grounded in Unit 3. So the solubility product expression for the dissociation of magnesium hydroxide in water would be magnesium times hydroxide squared. So now what we're going to do is, just like we did with KEQ, we're going to interpret these KSP values. So what does it mean to have a large KSP? What does it mean to have a small KSP? Now, we don't need to use the solubility product constant in the data booklet yet. We're going to use that for this part, but let's just think about what a large KSP value would be. A large KSP value would mean that there are lots of ions. Oh, I guess that's not what I wanted. More ions would be a better word there. More ions in solution. So the compound is more soluble than others, right? Whereas if you had a small KSP, then there are less ions in solution, meaning that the compound is less soluble. So the first table that we looked at, all it showed you was whether something would precipitate or not, right? So this table wasn't very specific. It's just like you're either soluble, meaning you would dissociate into all of your ions, or you had low solubility, and we were like, okay, well, you'd precipitate out. But even within the realm of low solubility, there's variable amounts of solubility. So this word low just means that it will dissolve or dissociate some, but the question is how much. This next table gives you more of an idea of how much it's going to dissociate. So in this next part, I've asked you, right, which of the following salts is the most soluble and which is the least? So let's look up each of these different salts, KSP. So this first one is copper 2 iodate. So we've got copper, alphabetical. Copper 2 iodate is here, and the KSP is 6.9 times 10 to the negative 8. The next one is calcium sulfate. So again, it's nice and alphabetical. So there's calcium sulfate, and it's 7.1 times 10 to the negative 5. Then we have strontium fluoride. Strontium fluoride, alphabetical, down here. Strontium fluoride has a KSP of 4.3 times 10 to the negative 9. And then lastly, magnesium carbonate up here is 6.8 times 10 to the negative 6. Awesome. Okay, so using this, which of them would be the most soluble and which one would be the least? So remember, the larger the KSP, the more soluble it is. So which of these has the largest KSP? Now it's hard because they're with negative exponents, but this is the largest KSP, so this would be the most soluble. The least soluble is going to be the one with the smallest KSP, which is going to be the 4.3 times 10 to the negative 9. So this is going to be the least soluble. So all of these substances on the first chart would say low solubility. And then of these, the strontium fluoride is the least soluble and the calcium sulfate is the most soluble. All right. So the next part of this is that the KSP value is constant. So if you increase the concentration of one ion, the other concentration of the other ion must decrease. What that means is that your solution can only hold so many ions, right? And so the KSP product has to be constant. So for example, if you look at this calcium sulfate, the product of these ions always has to be 7.1 times 10 to the negative 5. So if I was to introduce or increase the concentration of calcium in your solution, then it could hold less sulfate, right? So you'd have to remove or you'd have to decrease the concentration of the sulfate ion. It can only hold so much before it starts precipitating. Does that make sense? Hopefully. Okay. Now, the only thing that can change the value of KSP is, can you guess it? Can you guess it? What's the only thing that can dramatically shift things permanently? Hopefully, you're thinking temperature. All right. Oh, yay, that was our first lesson. All right, go practice those.